Good evening, ma. Good evening, everyone.
Good evening, sir.
Good evening, sir.
I think so. Last class we discussed about the octahedral void and all, right? Through the edge centered, we finished up to which only we finished. So we calculated number of voids. There are 3 voids are there due to edge centered because 12 edges are there. Then one edge is shared by 4 units. So totally 3 edges. So voids also divided into 4 parts. Then in the 3 edges, we have only 3 voids. Okay, likewise we discussed. The next one is a formula of a compound. What is the formula of a compound? You have to find out the formula of a compound. For that, we are in need of some details. Here, the particles should be packed in either CCC or HCP. Okay, CCP or HCP. Right. So here, contain 2 type of voids. We know that. What are the 2 type of voids?
Tetrahedral and
Tetrahedral voids and octahedral voids. Right. So tetrahedral voids are there and octahedral voids. Very good. So if suppose n number of atoms are there, there are 2n number of tetrahedral voids. Am I right?
Yes, sir.
These are all the things we already discussed. Suppose n number of voids are there, n number of octahedral voids are there. So which means that n number of atoms are present. So n number of atom means n number of octahedral voids. N number of atom means 2n number of tetrahedral. Then usually which void is a bigger one? Tetrahedral void or octahedral void? Which void is bigger?
Octahedral.
Octahedral. Which one? Tetrahedral voids are surrounded by only 4 atoms. Okay, 4 atoms, tetrahedral voids. But octahedral voids surrounded by 6 atoms. So more gaps will be here only. So octahedral voids is bigger one. And here just we are taken ionic compound like NaCl. You consider this NaCl. And here the smaller ions are called cations. The bigger ions are called anions. So here which one is anion? Na plus or Cl minus? Which is anion? In NaCl,
Cl minus.
Cl minus is an anion. So anion should be bigger in size. So the blue colors are Cl. The red colors are Na plus. Okay, the smaller ions. And usually the Cl minus ion, that means anions occupying at lattice point. Okay, we know that the tetrahedral voids are smaller than the octahedral voids. Yes. If cation is small, usually the cation anion will occupy lattice point. Lattice point. And what about this cations? They occupied in voids. They occupied in voids. If cations are smaller, then it occupies tetrahedral voids because the tetrahedral voids also very small. If cation is small, then it can occupy in that. If cation is big, that time it will occupy in octahedral voids. Okay. So we are comparing. Say for example, if we have a Na plus ions, Zn 2 plus ion, copper 2 plus ion, something like that. Okay. Suppose if I'm taking Na plus ion, if the size is very small, then it occupies in tetrahedral voids. Suppose if I'm taking Zn 2 plus or copper 2 plus, if the size are big, then it will be occupying in octahedral. Okay, so just we are not going to compare with only one solid. So this comparison is for different solids. Okay, if the cation is different, so if you have a different cation like Na plus, Zn 2 plus, copper 2 plus, then if the cation is very big, then it can occupy in octahedral void. If the cation is small, then it occupy in tetrahedral void. It's a general concept. And then void occupancy will give the formula of a compound. Yes, the void occupancy will going to give the formula of a compound. Okay, so formula of a compound, how we can check it? Formula of a compound. The void occupancy will give the formula. Yes. Now the compound is formed by two elements, X and Y. Okay, X and Y. Atoms of Y, that is anion, they can make CCP, which means that they are occupying at where it is going to occupy. Y, where it is going to occupy. Atoms of Y, where it is going to occupy, whether it is lattice site or voids.
Sir, can you repeat the question?
Lattice, sir.
A compound is formed by two elements X and Y. Atoms of element Y occupies, or atoms of element make CCP. Of those elements, X, that is cation, occupy all the octahedral voids. What is the formula of a compound? This is a question. How we can solve it?
So Y forms the lattice point for the structure.
Y forms lattice point. Why? Because I said earlier, which one will occupy lattice point? Cl minus. That means the anion will occupy at lattice point. Anions are going to occupy that lattice point. Cations are going to occupy it where? Cations are going to get occupied in voids only. Always cations are occupying in voids. If the void is small, then it occupies tetrahedral void. If the void is big, it will, sorry, if the cation is big, it will be occupied in octahedral. Okay. Now here it makes CCP, which means that it will be occupying the Y, which means that anions, which is occupying at lattice point. Okay, lattice point. Right. Now we can calculate the number of X. Number of Y means what?
Sir, what is CCP, sir?
CCP is cubic. What is that?
Cubic close pack.
Cubic close packing.
Okay. HCP means hexagonal close packed structure. Okay. So number of Y in CCP, how we can calculate? Cubic close packed structure and hexagonal close packed structure almost similar. Then the simple unit cell which will be using here is what? What kind of unit cell we can use it here?
Simple cubic.
FCC. FCC. No, it's FCC. Okay. So corner atoms. How many corner atoms? 8 corner atoms are there. And 6 face-centered atoms. 1, 2, 3, 4. Back of this, front of this. So what about the number of atoms in Y in CCP?
4 atoms.
4 atoms. Am I right? 4 atoms. How we can calculate? 8 corner atoms are there. 1 corner atom contribution is 1 by 8. We already discussed about the number of atoms per unit cell. Then 6 face-centered atoms are there. One's contribution is 1 by 2. So if you solve this, you can get 1 plus 3, that is equal to 4. 4 atoms per unit cell. We know that the value is 4. Am I right? We know the value is 4. You can take it as 4. Number of X. Number of X, how we can calculate? That is equal to, because what they said in the question itself, they given a clue. What is that? X occupy all the octahedral voids, which means that what? If n number of atoms are taken, n octahedral voids are there. Am I right?
Yes, sir.
Yes, sir.
So n number of X means number of octahedral voids. Octahedral voids. So then number of octahedral voids is equal to number of atoms, am I right? Number of octahedral voids, that is equal to number of atoms. What is the number of atoms we calculated? 4. So X is to Y, which is equal to 4 is to 4, which means that 1 is to 1 ratio. 1 is to 1 ratio, which means the formula of the compound is XY. Okay, the formula of the compound is XY. Is that clear?
Yes, sir.
So I have a doubt, sir. So here number of atoms, we take it as number of atoms of Y, no, sir. But we are taking it for the whole compound, right?
Which one?
The last
Number of
step.
atoms
Shouldn't-
means it's CCP only. Number of atoms per, yeah, it's for complete unit cell. Yes. I can't
Okay,
understand your question. Please, once more.
It's clarified. Sir. I understood now.
Clear or not?
Clear, sir.
Then atoms of element B forms HC, hexagonal close packed structure. And here it is from lattice. So B is a anion. Okay. And those of element occupy 2/3 of the tetrahedral. What is the formula of a compound by element forming by element A and B? So we know that B forms what? HCP lattice. HCP. HCP means what? So the same number of atoms are 4. Right? Here also we have a corner atom as well as face-centered atoms. Just assume it here. So 1, 2, 3, 4, 5, and 6. Here also number of atoms are 4. 4 atoms per unit cell. Yes, we have taken. So B value is almost 4. Okay. Sorry. So B forms HCP. That value will be taken as 4. Okay. Just we can take it as X. Okay. And A occupy 2/3 of tetrahedral void. So how many atoms should be there?
Two and
So
atom.
number of A is what? 2/3
2 into 2.
tetrahedral voids. Am I right? We know that this is the given formula. This is the formula. This is the data given in the problem. And we know that if number of atoms are A, if the number of atoms are N, 2N number of tetrahedral voids are there. Okay. Then we can calculate 2/3 into 2x. Okay. So what about the total? That is 4x/3. That is the A value. Is that clear? A value will be taken as 4x/3. Why? Because number of atoms are A means 2N number of tetrahedral voids should be there. But here the tetrahedral voids occupied by only is 2/3. So 2/3 into 2. Okay. So total A value is 4x/3. Then if you want to calculate the ratio A into B, so 4x/3 is to x. We know that x value we have taken as the x. Then what is the formula? 4x is to 3x. Okay, which will be taken as, you consider this A, this is B. So in the ratio 4:3 ratio, so we can get the formula A4B3. This is the formula of a compound. This is the formula of a compound. Is that clear or not?
Sir, can you explain that number of A, that steps, sir? Where you took
Number
A
of
is equal
A
to 2 by
step.
3 into 2x.
Okay. Number of atoms, that is equal to 2n number of tetrahedral void. Am I right? If number of atoms are A, then 2n number of tetrahedral voids. So already it occupied only 2/3. So into 2, if you put it, you'll get the same number of voids. Okay. The tetrahedral voids we have to calculate. That's what we are multiplying with 2. Why? Because if n number of atoms are there, 2n number of tetrahedral voids are there. Okay.
Okay, sir.
And next one is the packing efficiency. What do you mean by packing efficiency? Packing efficiency is the percentage of total space filled by particles Particles mean what? Constant particles. Maybe atom, ion, molecule, whatever maybe. The percentage, packing efficiency is nothing but the percentage of total space filled by the particle. So always we have some empty spaces if you pack it in any way. Even we are packing with the square close packing. We have a packing with a hexagonal close packing, HCP structure, and then square close packing structure. In all the cases, we have some empty spaces. But here the empty space is large, here the empty space is less. That's the difference. But definitely we have empty space. Why? Atoms are considered as a sphere here. Okay. Atoms are considered as a sphere. That's what definitely the gap should be there. Okay. So we have to calculate the percentage of filling of space. That is what the packing efficiency is done. Packing efficiency in HCP or CCP structure almost gives 74% efficiency. Then packing efficiency in BCC structure, that will be given almost 68%. The packing efficiency in simple cubic structure is what? That is almost 52.45%. Almost below 53%. Okay. The lesser efficiency will be there because we know that this is if it is a face centered at HCP lattice or CCP lattice means we have to use face centered unit cell, right? Here BCC unit cell. So BCC unit cell, if we use it, the number of atoms are very less, only 2 atoms. Here 4 atoms. Here only 1 atom. Okay. So number of atoms per unit cell, the density is getting decreases. That's what the percentage of filling also getting decreases. So packing efficiency. And the packing efficiency in HCP structure. HCP structure, how we can calculate it? So we know that if you want to calculate the packing efficiency of any structure, we must know the two things. One is A value. What is the A value? The A value is nothing but edge length. What do you mean by edge length? Edge length is what? What is
dimensions of the cube?
Sorry?
Dimensions of figure.
Dimensions of the figure. Okay, fine. You can calculate the dimensions of the figure. Okay, just a minute. Okay. So the dimensions. Okay, fine. If you want to calculate A value, how we can find out? Whether we can measure directly here. Is it possible to measure here? A is what? This is A. This is a edge length. A value. And this is also A. Right? This is A value. And this is also A. Whether we can calculate perfectly here. Whether we can calculate this length perfectly from this end to this end. We can't get it. Why? Because here we have some empty space. Here we have some empty space between them. That is what we don't know about the empty space between that two atoms. Okay? Is it clear or not?
Can you explain consequence?
Yeah, no problem. So we need to calculate the dimensions of the unit cell. If we want to calculate the dimensions of the unit cell, how will we calculate? If you want to find out the volume of unit cell, what is that? A cube. Am I right? A cube. Why? Because here A equal to B equal to C. But here A equal to B equal to C means A will be taken as A and B will be taken as B. Sorry, A and C also will be taken as A. That is what will become A cube. A into A into A. Okay. So length, breadth, and height will be taken as, and that is what it can give volume. So we can get A cube. If we want to calculate the volume, we can get, we have to use the A cube form. So we are in need of calculating A value. How we can find out the A value here? How we can find out the A value here? So we can't directly measure here because there will be a gap will be there. So from this end to this end is called A value. Am I right? That's a edge length. But here between these two atoms, there will be some empty spaces there, but we can't predict what is that space between them. Okay, that is what we have to calculate. What is that edge length in terms of radius. In terms of radius, we have to calculate the edge length. How we can take edge length? Say for example, so here the gap is there. Here the gap is there. We can't predict. Here also gap is there. Here also gap is there. So we are in need of calculating the edge length in terms of radius. So sphere has radius. We know that. Here you just assume it here. This is the length. This is the triangle we have taken. This is the triangle. Okay, this is the triangle we have taken. Now this is A, and this is also A. We know that, and this will be taken as B. We know that Pythagoras theorem. So if we know that B square, that is equal to A square plus A square. What is that? Two sides of that square, which will be equal to one side of the square. Am I right? So B will be taken here, and here it will be taken as R. What is the R? Radius. Here one full atom will be there. The orange, sorry, yellow color is there. One full R. That is what 2R will be taken. And here also 1R will be there. Radius. So here B square is equal to 2A square. From this one A and this one A will be there. So totally 2A square. So according to that, if you want to calculate the formula for B, that is equal to root 2A. Am I right? So this is a value I'm getting. And what about that B? B also will be in terms of radius we have taken. B that is equal to 4R. Now this B and this B both are equal. So 4R that is equal to root 2A. So just I have to calculate the edge length here. What is the formula? 4R by root 2. This is the formula of calculating edge length. So first of all, edge length we can't directly taken from that unit cell. That's what we have to take the radius. In terms of radius, we have to calculate the B value. So once you got the B value, after that, it will be equated with 4R as well as root 2A. Okay. So from the, in terms of radius only, we are calculating the edge length. So now we can do the packing efficiency for the packing efficiency. What is the formula for packing efficiency? It's nothing but volume of sphere divided by volume of cube into 100. 100 is for percentage. Okay. So volume of sphere, how we can find out? So if you want to find out the volume, what you have to do? Number, how many number of atoms are there, and then its volume. That is 4 by 3 pi r cube. Okay. So we can use it. So how many number of atoms are there in this particular unit cell? We know that it is a FCC unit cell. So we have 4 number of atoms. Number of atoms are 4. 4 number of atoms are there. So 4 into 4 by 3 pi r cube divided by volume of cube. We know that it is A cube. Okay. So A into A into A. That will give A cube. What is the value? 4R by root 2. A value is 4R by root 2. So 4R by root 2, the whole cube I can take. 4R by root 2, the whole cube into 100. To solve this, you will get 74%. Is that clear? This is what you have to calculate the packing efficiency of HCP or CCP structure given to you. If the given HCP structure or CCP structure, you have to calculate edge length in terms of radius. After that only you have to mix it with the formula.
Sir?
Yes.
Sir, how you took B as 4R, sir?
That is what radius means. Because here the only touching atoms. So here in terms of radius, we have to calculate it. Okay. So here there is a gap. So we are unable to find out the A value exactly. That is why we have taken a triangle this. Okay. And here 1/8 part of the atom will be there. Okay, 1/8 part of the atom means this is the center of the atom. Okay, center part to the corner part is radius, right? And here one full atom is there, that is 2r. So this is center part, one half this, one half here. So that will be taken as 2r. And here also 1/8 part of that there. So this is also 1r. Because this triangle, why I am taking this triangle here? Why I am taking this B here? Because this is the only touching possibility. All the atom, this red color atom touching with this one, and this atom will be touching with this one. There is no gap between them. That is what we can calculate the radius. Is that clear?
Yes, sir.
This is R, this is 2R.
Yes.
Full atom is there, this is R. So totally 4R. So 4R is equal to root 2A. So we can calculate A value. So from that A, we can calculate A cube. That is the packing efficiency almost 74%.
Okay,
And
sir.
packing efficiency for BCC structure. So what about the BCC structure? For BCC structure, how we can calculate the BCC structure? Here also the same thing, am I right? How we can calculate for BCC structure? So here also the same problem is existing. Edge length, we can't calculate it. In all the direction, we can't calculate the exact edge length because we have some gap in between them. We are not able to predict the edge length properly. Then how we can do this? How we can do this, Kana? By making the
You draw
same
diagonal, sir.
in terms of, yes, we have to take a diagonal. So by the way, we can calculate in terms of radius only we have to move that. Okay, we have to move it in terms of radius. Yeah. So here we have to take this diagonal, right? This diagonal, this triangle. Because this is a only touching possibility is there. Am I right? This is what I'm showing here. Here one atom is completely touching. This 1/8 part of the atom will be touching with this whole atom, and this whole atom is touching with the diagonal. Okay. Now how we can calculate that? We know that this is one edge length, and this is one edge length, and this is one edge length. If you want to calculate this diagonal, okay, and this will be taken as B, and this will be taken as 2A because 1A and 2A. Okay, and this is third A. So B square that is equal to 2A square plus A square. Okay, is that clear or not?
You can repeat again why you took 2A.
Because we are taking diagonal atoms, right? If you take a diagonal atoms, here one edge length is here, one edge length is here. This is 2A square, and this is also 1A square. So the total is 3A square. The entire thing is B, that is B square. So B square that is equal to 2A square plus A square, or B that is equal to root 3A. Is it clear or not? Is it clear or not?
Yes, sir. Sir. Yes, sir.
Yeah. Okay. Now here also the same thing. Here 1R is there. That is a radius. Okay. Center of the atom to the corner. So one radius. And here one radius. The center is radius. And here one radius. So radius 2R. And here also 1R. So totally B that is equal to 4R. In terms of 4R we can take. And what about the next one? So we have to equate these two B values. That is 4R that is equal to root 3A. So A that is equal to 4R by root 3. Is that clear? Is that clear, Kana?
Yes, sir.
Yeah. So if we calculated A value, we can calculate A cube also. That is 4R by root 3, the whole cube we can calculate. Then as usual, packing efficiency, we know that. So number of atoms, how much here, Kana? for this particular unit cell BCC? If we take in BCC unit cell, what is the number of atoms?
2 atoms.
2 atoms. So 2 number of atoms. Why we are taking this 2? Because we have to calculate the entire volume. So we have to know how many number of atoms are there. So 2 number of atoms into 4 by 3 pi r cube divided by a cube. A cube is what? 4r by root 3 the whole cube into 100. If you solve this, you will get 68%. That is the packing efficiency of this one. Okay. The next one is packing efficiency for simple cubic. How we can calculate this is very simple, right? Because there is no gap between that atoms. Each and every atom will touching with each other. Why? Because the simple cubic structure. Okay, because no atoms are in between them. That is what here the value is a value. We can calculate it directly, or we can take it as a value as 2r. Am I right? A value will be taken as 2r because this is 1r, this is 1r. The whole thing is a. So a that is equal to 2r. So a cube we can calculate 2r the whole cube. Is that clear? So here the packing efficiency is nothing but 1 into 4 by 3 pi r cube because number of atoms are 1. Why? Because only one atom present in the unit cell. Because the simple cubic. Then divided by 2r the whole cube. Resolve into 100. Resolve this, you will get 52.45%. Is that clear, Kana?
Yes, sir.
Is that clear or not?
Yes, sir.
Yeah. And next one is formula of a compound. We know that we calculated already the formula of a compound. And next one is the density, dimensions of unit cell. How to calculate the dimensions of unit cell? What do you mean by dimension of unit cell? Dimension of unit cell. How will you calculate the dimension of unit cell? Calculating unit cell dimensions. How we can?
Finding the volume of the cube.
Okay, calculation of dimension of unit cell. Which means that we can calculate the density of unit cell also we can calculate by using this formula. So we are going to derive the formula for density. What is the formula for density? It's nothing but mass by volume. Am I right? Mass by volume, we know that. Okay. So here Z based on Z is nothing but number of atoms. If it is a simple cubic, the value is. If it is a simple cubic, the value is 1. Am I right? 1. If it is a BCC structure, the value is 2. If it is FCC or HCP structure, the value is 4. The number of atoms are 4. Am I right? So based on that, we can calculate the power. So here we have to calculate the mass of unit cell. So here we are going to calculate the density of unit cell. So we are in need of mass of unit cell. Mass of unit cell, how we can calculate? By volume of unit cell. Mass of unit cell, how we can calculate? Number of atoms, right? Number of atoms into mass of one atom, right? Mass of one atom. Okay. So number of atoms into mass of one atom, that will give mass of unit cell. Is that clear or not? Say for example, you just take this a unit cell. So we have many number of corner atoms, 8 corner atoms are there. So here we have to calculate number of atoms. How many number of atoms are here? 1 atom. So if you know that mass of 1 atom, we can find out the mass of entire unit cell. Am I right?
Yes.
If you have, suppose if we have body centered unit cell, so corner atoms are there and one entire center, we have one atom. So this is a body centered unit cell. Am I right? Here we have to calculate number of atoms. 2 number of atoms are there into mass of 1 atom. Mass of an atom. Mass of 1 atom into 2, that will give 2 atoms. So the entire the unit cell contain only 2 atoms. So we can calculate total number of, total mass of unit cell. Am I right? Is that clear, Kana?
Yes, sir.
So I have a doubt, sir.
Yes.
So suppose it's an ionic compound, sir, then how should we calculate? So there'll be two different masses.
Sorry.
If it's an ionic compound, so there'll be two different masses, right, sir?
2 different masses there. Okay.
Yes, so like NaCl, we'll have a different mass for Na and Cl. Then how do we calculate density?
But here we are going to calculate only the things which is present in the corner as well as what is that? A corner which is going to, which one is going to form lattice site. So suppose if I'm taking
ignore the
NaCl,
anions, sir.
yeah, it entirely depends on anions. Okay. So number of atoms into mass of 1 atom, that will give mass of unit cell. Okay, mass of unit cell. We can calculate. Number of atoms we can take it as Z. Okay, Z. Mass of atom is nothing but mass. We have taken as molar mass. Okay. Volume of unit cell. How we can take volume of unit cell? So if we want to calculate number of atom, mass of 1 atom, how we can calculate molar mass by Avogadro number? Am I right?
Yes, sir.
Avogadro number. And volume of unit cell now. Volume of unit cell. How we can calculate? Volume of unit cell is nothing but A cube. Am I right? So what will be the formula? So if you want to calculate the density, so Z into mass by Avogadro number, the whole divided by A cube. Okay. So which means that A cube by 1. Okay. So Z into M by NA into A cube. Am I right? So Z into M by Avogadro number into 1 by A cube. So if you taken this into numerator, it become 1 by A cube. Now the formula will be like this. This is the formula for calculating the density of unit cell. From that, we can able to calculate. They can ask many questions. They can ask either molar mass to. They can ask you to calculate molar mass. Otherwise, what type of unit cell is this? Or they can ask density. Or they can ask volume of unit cell also. Okay. The problems will be given. Any one of the things will be given to you. Any one of the things will not be given to you. You can able to calculate other things by using this formula. Okay.
Sir,
Yes.
sir, here is the number of atoms per unit cell or the total number of atoms?
Number of atoms per unit cell.
Okay, sir.
Yeah. Because we are calculating mass of 1 unit cell, density of unit cell only. Okay. And next one is based on this, we can have some problem. That is an element has BCC structure with cell edge 288 picometer, density of element is 7.2 gram per centimeter cube. How many how many atoms are present in 208 gram of element. They given the mass of element. So we have to calculate for this particular mass, we have to calculate how many number of atoms are present. What are the things given to you? Here the A value is given. Am I right? A value is given. What is that? 288 picometer. Okay. And density also given. What is that value? 7.2 gram per centimeter cube. And we know that a density that is equal to mass by volume. Am I right? Mass by volume. How we can calculate the density is given to you, but we have to calculate what? We have to calculate the volume of 1 unit cell. Volume means how we can change the formula. So, but they ask you to calculate the volume of 208 gram of unit cell. So, volume of 208 gram of element, that is equal to mass by density. Am I right? Mass is what? 208 gram by density is what? 7.2 gram per centimeter cube. Gram cancel. You solve this, you'll get some volume. Okay, that is called 28.88 centimeter cube. So the volume will be given in centimeter cube. Okay, so the volume of 1 unit cell. Volume of 1 unit cell is what? Unit cell is A cube. Am I right? So the entire value, that is 288 into 10 power minus 10. Why we have to put 10 centimeter cube? Because the volume will be given in centimeter cube. That is what we have to convert this into centimeter cube. Because picometer is what? 10 power minus 12. So we have to convert this into centimeter cube. That's what we are having, 10 power minus 10. Solve this, you will get 2.39 into 10 power minus 29 centimeter cube. Okay. Then we know the volume of 1 unit cell. Then we can calculate number of unit cells which is present in 208 gram. So total number of unit cell divided by volume of 1 unit cell. Total number of unit cell divided by volume of unit cell. Volume of 1 unit cell. So we know that the value is 28.88 centimeter cube divided by 2.39 into 10 power minus 29 centimeter cube. Centimeter cube will get cancelled. If you solve this, you will get 12.08 into 10 power minus 23 unit cells. So this much of unit cells are there. So what is that nature of unit cell they given? BCC structure. We calculated number of unit cells. And if you if a BCC means, what is the number of atoms for BCC? Atoms in BCC is what? 2. Am I right? So we know that if 2 into number of unit cells, that will give total number of atoms. Okay. N number of atoms means 2n number of tetrahedral voids. Okay. You should keep this in mind. So here, if number of atoms in BCC structure, we know that unit cell. Number of unit cell is here, but here number of atoms they are asking. So 1 unit cell contains 2 atoms. So then unit cell into 2, that will give number of atoms. Okay. So 2 into 12.08 into 10 power 23. So if you solve this, you will get 24.16 into 10 power 23 atoms. This is a number of atoms. You have to calculate by using this form. Okay. Is that clear, Kana? If you have any doubt, you can ask.
Sir, here we are calculating the total number of units only, no, sir.
Total number of units.
Unit
Yes.
cell only, right, sir? Sir, then why are we dividing the total volume divided by the volume of one unit cell, sir?
Total number of unit cell, because we need to get number of unit cell. Total number of unit cell we have. Okay. If it isn't divided by volume only, we can get the number of unit cell.
Sir, so the volume is equal to the number of atoms, right? Okay, sir.
That is what we are calculating. And next one is an X-ray diffraction studies. XRD, they can say XRD studies. X-ray diffraction, otherwise called as XRD studies. Shows that copper crystalline in a FCC unit cell. So here the number of atoms are 4 with edge length. With edge length 3.608 into 10 power minus 8 centimeter. In a separate experiment, copper is having density of 8.92 gram per centimeter cube. Calculate atomic mass of copper. Calculate atomic mass of copper. How we can calculate? So we know that what all the things given to you is that they given. Z is equal to 4 because they're not giving directly. FCC is given. FCC means it is 4. Then density D they given. What is that? 8.92 gram per centimeter cube they given. And what about the another data given? Edge length. A is given 3.608 into 10 power minus 8 centimeter they given. Okay. So now what we have to calculate? We have to calculate mass of copper. That is molar mass. Okay. So how we can calculate? So we know the formula D is equal to Z into M divided by Na, Avogadro number into A cube. But we need to calculate is what? M. M we have to calculate. So we have to change the formula as density into Avogadro number into A cube divided by Z. So we know the value of density. Density is what? So 8.92 gram per centimeter cube into Avogadro number is what? 6.023 into 10 power 23 atoms per mole. They give into A cube is what? 3.608. 3.608 into 10 power minus 8 the whole cube into centimeter cube divided by total number of atoms are what? 4 atoms. Okay. Now we can cancel the centimeter cube per centimeter cube cancel. Atoms getting cancelled. Then only unit is the gram and mole. So we know that molar mass unit is gram per mole. We solve this, you will get 63.1 gram per mole. That is the mass of copper. Okay. Is that clear?
Yes, sir.
Then silver forms, Ag forms CCP lattice. And XRD shows Just a minute. Shows that edge length of its unit cell is 408.6 picometer. Calculate density of silver if the atomic mass is given. Atomic mass of silver is equal to 107.94 gram per mole. Okay, these are all the things given to you. So then straight away we can calculate Z value. We know that is 4, and we know that edge length A also we know that is 408.6 picometer. Then atomic mass also they given, that is 107.94 gram per mole will be given to you. So we know the formula for calculating density, that is density that is equal to Z into what is that M, am I right, divided by Avogadro number into A cube. So Z we know that is 4 atoms into M is given, that is 107.94 gram per mole is given to you, divided by Na is what, 6.023 into 10 power 23 atoms per mole will be given into A cube. A cube is what, 408.6, the whole cube into centimeter cube. Okay, into 10 power 10. Sorry. Into 10 power minus 10, the whole cube centimeter cube. Okay. So now we can calculate the density. So we can cancel the common things, atoms, mole per mole, both are getting cancelled. Gram per centimeter cube is the remaining one. If you calculate it, you will get 10.5 gram per centimeter cube is a density of silver. Density of silver will be like this. So just a direct formula. No need to change anything in the formula. Just you can do substitute the values. Then you can get that.
Sir, this unit is universal, no, sir? Like, we can use it for all the sums asking to calculate the density, right, sir?
Yeah, almost. Then a compound forms. So compound, CPD means a compound. Compound forms HCP structure. HCP structure. What is the total number of voids? What is the total number of voids? In 0.5 moles of it. And they're asking how many of these are tetrahedral voids. Yeah, how we can calculate? So we know that n number of atom means 2n number of tetrahedral voids. We know that. So what is the n value here? Number of atoms.
0.5.
Number of
0.5 into 6.022 into 10 to the power.
Yeah, fine. So we know the number of atoms I'm asking. Number of atoms. Number of atoms per unit cell for HCP structure is 4. Okay. Number of atoms for HCP is what? Is equal to 4. Is equal to 4. Am I right? So here they given 0.5 moles. 0.5 moles means what? 0.5 into 6.023 into 10 power 23. atoms per mole or mole or atoms per mole, we can see atoms per mole. Here 0.5 moles will be there. Okay. Then mole per mole is getting cancelled. If you solve this, you will get 3.011 into 10 power 23 atoms. Okay, 0.5 mole means what? 3.011 into 10 power 23 atoms. What about the n number of atoms? If I have a n number of atoms, n number of tetrahedral voids are what, Kana? 2 into 3.011 into 10 power 23 atoms. We solve this again, 6.023 into 10 power 23 atoms. Okay. Okay, because sorry, atoms, not atoms, voids.
Sir, is it 6.023 or 022?
023 approximately. Okay.
Oh, okay, sir.
Yeah. So 6.023 into 10 to the power of 23 voids will be there. Okay. And one more problem we'll have. Yeah, this is a very important problem. In every model, I will do one problem. Okay. An atom, an element with molar mass. They given molar mass here. Molar mass 2.7 into 10 power minus 2 kg per mole will be given. Forms a cubic unit cell. Cubic unit cell. So they are not mentioning any cubic unit cell, whether it is simple cubic or body centered cubic or face centered cubic. They are not telling. So they are not giving even a structure also, right? Whether it is simple cubic or BCCA or HCP or CCP, they are not mentioning anything. They are giving as simple, that is a cubic unit cell they give. With edge length. With edge length 405 picometer. If its density is 2.7 into 10 power 3 kg per meter cube. What is the name of unit cell? What is the name of unit cell? How we can calculate it, Kana? What do you have to find out here?
We define Z, sir.
Yeah, very good. So if you find Z, if the value is 1, it is simple cubic. If Z is equal to 2, then it is BCC. If Z is equal to 4, then it is HC. Okay. So we have to calculate Z. So what are all the things they given? They given A value is given. A is equal to 405 picometer. And then density they given, that is 2.7 into 10 power 3 kg per meter cube they given. And they given molar mass also. Mass that is equal to 2.7 into 10 power minus 2 kg per mole also they given. So we have to rearrange the formula for Z. So we know the density formula, that is m into Z by Avogadro number into a cube. That is equal to. So if you solve it for Z, then the formula will become like this. Yes. D into Na into a cube divided by mass. Okay. What is the density? The density value given, that is 2.7 into 10 power 3 kg per meter cube. Kg per meter cube? No, kg per mole, right? Here the kg per mole only given. Sorry, meter cube only. That's the density. Meter cube, they give. into Avogadro number 6.023 into 10 power 23 atoms per mole into A cube. A cube, how we can calculate? Here we can take it as here the meter cube is given. It is given in meter cube. So we can keep the value in meter cube also. That is 405 into 10 power minus 12. The whole cube centimeter cube. Okay. Divided by whole divided by molar mass.
It should be meter cube, right, sir?
Sorry?
405 into 10 power minus 12 meter cube, right, sir?
Yeah, sorry. Meter cube. Meter cube only here also. So here we can kg is getting cancelled. Then mole per mole is getting cancelled. Meter cube is getting cancelled. We can calculate the density of we can calculate Z in terms of atoms. To solve this, you will get 384 into 10 power minus 12, minus 2 atoms. So this is approximately which is equal to 3.84. Okay, the 3.84 approximately equal to 4 atoms. If the number of atoms are 4, either it may be HCP or CCP state. Okay, so by that way we can calculate what is that number of atoms. So we can find out that nature of cubic units. What is that here, HCP or CCP? Okay. The next one is the imperfections of solids. What do you mean by imperfections of solids? Suppose if I'm taken some ionic solids like NaCl, it also has some impurities. Why? During the crystallization process, the impurities can also accumulate. Okay. So if the crystallization process, if the crystallization is too fast, it forms amorphous solids. Am I right? Amorphous solids. If crystallization process is too slow, then it forms crystalline. If it is not fast and not too slow, not too fast and not too slow, it's an average speed or in slow speed, then it forms imperfections. Because it requires some time to settle. Only one by one, slowly, very, very slowly, the particles are settled and they can form crystalline solid. The similar pattern of arrangement will be there. But here in the case of amorphous solid, there is no respective time will be available to settle the particles. So it can arrange it in like this. Okay. So the order of arrangement will not be in proper manner. But here imperfections, it can be settled slowly, but the impurities can also occupy their positions. Okay, that is what the solids are getting, some imperfections. Generally, this will be otherwise called as a defects. Defects. What do you mean by defects? So the defects creates irregularities in the arrangement. Irregularities in the arrangement of particles, constant particles. So here generally the defects can be divided into two types. One is point defect, another one is line defect. Point defect, another one is a line defect. But in your syllabus, they're not focusing that much on the line defect. So what is line defect? That is the only thing you should know. Then the point defect, you should know in depth. Because a point defect, we have two categories. What all that? One is stoichiometric defect, non-stoichiometric. Stoichiometry, so which will be if it affects stoichiometric, the stoichiometric, and if it is not affecting, then non-stoichiometric. And here in stoichiometric defect, point defect, we have category. What are all that? Stoichiometry and non-stoichiometry. Stoichiometry and non-stoichiometry. In the stoichiometry, we have number of classification, vacancy defect. So let's see one by one. vacancy defect, interstitial defect, Frankel defect, Scotty defect, Schottky defect like this. Okay, we have even metal deficiency defect, metal excess defect. We have number of classifications. So one by one, first one is a point defect. What do you mean by point defect? Only one particular point will be getting affected. Okay, so only this point is missing. Okay, the or either missing or instead of this particular point, particular atom or particular ion or particular molecule, some impurities may be present. That is called point defect. But line defect is not like that. So here we have 4 lines. I mean, like 4 rows are there. Here also 4 rows. Here also 4 rows, and what entire row is missing here? Only 3 rows. So in that missing row, impurities can get up. That is what it can produce line defect. Okay. So point defect will be taking place at a particular point. Say for example, only this particular point is missing. That is coming under the category of point defect. For line defect, the entire row is missing. Complete row is missing. Instead of that, it may be some impurities may also be present. And here point defect types, the first one is a vacancy defect. So this is a vacancy defect. So one atom is missing here. Okay, one atom is completely missing. That is called a point defect, in which we have vacancy defect. This is otherwise called as a vacancy. So vacancy defect will decreases the density. Am I right? Decreases the density of the crystal. Why? Because something is missing.
There's free space.
Something has to be there, but something is missing. That's what it decreases the density. The density is getting decreases. And because some lattice points, some lattice sites are vacant or becoming vacant. That's what may be called as a vacancy defect. Usually where it is taking place, non-ionic crystals will form these kind of defects. Non-ionic solids or non-ionic crystals will show these kind of point defects. Okay, this then decreasing in density will be there because of vacancy position of one atom or a molecule. And next one is the interstitial defect. Interstitial defect. So in between the 2 rows, one excess atom will be there. That will be acting as impurity. The impurity will be placed in the interstitial position. Interstitial position is nothing but 1 row and 2 row. Between that 2 row and one atom is located. Okay, likewise here also. Okay, these kind of things. And these are all interstitial sites. And these interstitial positions will be occupied by one excess atom. So here what will be there? Whether it increases the density or decreases the density?
Decreases, sir.
Increases. Why? Because one excess
But there's
atom is
space,
located.
right, sir?
Apart from this, one excess atom is here.
Next
This is the
to the atom, there's space, right, sir? So the
Yeah.
area occupied decreases.
area occupied is decreases. No, actually, this is shown for the understanding only. Okay. Now normally this much of space will not be here. Okay. Normally this much of space will not be here. It increases the density because this is a constant particle. This is a A row. This is a B row. Between these 2 rows, some in that interstitial position, this impurity is occupied. Okay.
Okay, sir, understood.
Here constituent particles are occupying interstitial site. So when excess atoms excess atoms or excess constituent particles are in unit cell or crystal, whatever. Okay. Interstitial position, some of the atoms are located. Okay. And then occupying at interstitial site also. Interstitial site in the sense, for example, we have some unit cell here, 1, 2, 3, 4, and we have 1, 2, 3, 4 number of atoms. If you're connecting all those things, we'll get some lattice points. So in between them, we have some interstitial sites. In that interstitial site, that impurity will going to occupy. And generally, it increases the density of the crystal. Okay, that is what interstitial defect. And next one is a Frankel defect. What do you mean by Frankel defect? Normally, the previous one also will be taking place in non-ionic solids. Non-ionic solids. But here, Frankel defect and Scotty defect are taking place in ionic solids. Say, for example, if I'm taking NaCl, okay, all are charged particles, right? Here you are considered as a negative charge, positive charge, negative charge, positive charge, negative, positive, negative, positive. So blue color atoms are positive atoms and red color atoms are negative atoms. And usually we know that negative atoms are bigger one, okay, and positive atoms are smaller one, okay, smaller one. But here I'm not giving like that. So because that will create a lot of confusion. That's what I'm not giving like that. So here it should maintain. It must maintain neutrality. What do you mean by neutrality? What do you mean by neutrality?
Excess of positive and no excess of negative.
Sorry?
So there should be equal number of positive and negative.
Yeah,
charges.
very good, very good. Number of anions, that is equal to number of cations, right? Number of cations. That is called neutrality. That means the charges are equal. Number of positive charges is equal to number of negative charges. And the Frankel defect is nothing but the smaller ion is dislocated. You have to carefully listen the word dislocated from original position to interstitial site. Interstitial sites. Okay. So suppose one negative ion is removed from that original position and that can be occupied that interstitial point. If negative ion went, suddenly another negative ions, okay, another positive ion will also be, okay. So here, what is that? It should maintain electrical neutrality. If one negative ion is went to the interstitial position, another positive ion will also should go, okay. It's missing actually. So suppose this ion will also occupy this position, this ion will also occupy this position. Two red color atoms are occupying that position, and two what is that? Negative ions will also be occupied. Actually, it's not. Okay. So maintaining neutrality in the sense what? Positive charge which is equal to negative charge. Okay. Number of positive charge which is equal to number of negative charge. Here only shifting of smaller ions will be taking place. That is what? That is the difference between Frankel and Scotty defect. Okay. Frankel defect, only smaller ions are dislocated. So they are going to get occupied in lattice position. Sorry, interstitial position. Okay. So now also the number of positive charge and negative charges are equal because it is located in the interstitial site instead of its lattice point. Okay.
So I have a doubt, sir.
Yes.
So you can say this is a combination of vacancy defect and interstitial defect, sir.
Combination of
vacancy defect and interstitial defect.
No, it's not vacancy defect. Vacancy defect means one complete atom will not, which will be completely removed from the crystal. But here it will be removed, but removed atoms or ions which will be located in interstitial point. In generally, vacancy defect will be taking place at non-ionic solids. But here, ionic solid, this kind of defect will be taking place. Okay.
Okay, sir.
And next one is Scotty defect. What do you mean by Scotty defect? Yeah, I'll show. Here, what is Scotty defect? Here also, negative, positive. Right? Here, where I put negative? So I put negative here. Am I right? Negative, positive, negative, positive, negative, positive, negative, positive. Yeah. Here, what kind of defects are taking place? Scotty defect. So once the Scotty defect, it is nothing but a missing of ions. Sorry, missing of ions. Missing of ions. So in Frankel defect, we have what that is a dislocated from original position to where interstitial site. But here the missing of ions, entire atom is going to miss. And here also the neutrality should be made. Neutrality is maintained. Neutrality is maintained. Here, the number of cation, which is equal to number of anions. At the same time, number of cation missing, which is equal to number of anion missing. Anion missing. You clear? So that is a neutrality. Okay, that is a neutrality. Say for example, if one positive ion is missing from here, say for example, here I am having positive ion, one negative ion will also getting missed. Here it is a negative ion. Here I have a negative ion. Okay, and one more positive ion is missing, and one more negative ion is going to miss. Okay, now you can consider. So if one positive ion is missing, one negative ion is one positive ion missing, one negative ion missing. And here it decreases the density. Decreases the density of the system. But it maintains the neutrality. Okay, it maintains the neutrality, but density of the system is getting decreases. Why? Because atoms are going to miss from the system. From the system, the atoms are removed. Okay, so only difference between Scotty as well as Frankel defect is there only smaller atoms are smaller ions are dislocated, but here both ions are missing, which means that almost equal sized anions and cations are present here. Okay, so even say for example, if you take Na plus Cl minus, Na plus size is very small, but Cl minus size is very big. That will involving in Frankel defect. Okay, but Scotty defect, almost equal sized cations and anions are involving because both the atoms are going to miss. Okay, both the atoms are going to remove from the system. That's what is called Scotty defect. Okay. Next one is a impurity defect. What is the impurity defect? So this is due to some foreign substance. And that will act as an impurity. Due to that, the defects will be arises. That is called what is that? Impurity defect, we can say. So here I have taken you consider this as a Na plus ion and Cl minus ion. So the crystal is NaCl. Okay, I have taken NaCl. I have taken molten NaCl. Molten NaCl means what? Molten NaCl means what?
Sir, could you repeat the question?
So what is the meaning of molten NaCl? That's what I asked.
Liquid NaCl, sir, due to heating.
Liquid NaCl, right? Liquid NaCl. If NaCl is heated and that become a melt of NaCl, that is called molten NaCl. Okay, molten NaCl will be taken. And the molten NaCl will be taken. And now, if it is molten, in that molten NaCl, just I'm adding very little bit of amount of SrCl, strontium chloride salt. That will be acting as an impurity. Okay. So what is the charge of Na plus and Cl minus? And here, what is the charge of Sr? Sr2 plus. Oxidation state will be varied because it's a divalent cation. It is a monovalent cation, right? So Sr2 plus. Suppose you consider here, you add one Sr2 plus ion to the system. How many Na2 plus Na plus will has to come from the system? So charges should be equal. Yes, because impurity defect also the charges should be equal. Number of positive charge equal to number of negative charge. Right? Because the ionic solid. So if you add one Sr2 plus to the system, so now you are adding one Sr2 plus to system. So what about the charge of Sr2 plus? It has 2 plus charge, but Na has only 1 plus charge. So 2 Na plus has to come from the system to neutralize the charge of 1 Sr2 plus. Am I right? If 1 Sr2 plus, if I'm adding to the crystal, then what will happen? 2 Na plus has to come from the system. Okay, like this. Okay, say for example, you are consider these are all this is a 1 Na plus and this is also 1 Na plus. Both has to come from the system, and Sr2 plus will occupy any one of that position. Okay, because only one Sr2 plus is there. One Sr2 plus which is going to add in that position. Then what about the remaining? One Sr2 plus is added here. Then what about the remaining thing? One Na plus position will be unoccupied. Okay, which will be unoccupied. That is what? So the cation, here Na plus is there now. That is cation. That is what is called cationic vacancy different. Is that clear or not? Able to understand this or not? Very simple. So molten NaCl are taken and then adding small amount of strontium chloride also. If I'm adding strontium chloride, so Na plus Na has only 1 positive charge. Sr has 2 positive charge. And if I adding 1 Sr2 plus, the charge neutrality should be maintained in the crystal. That's what 2 Na plus has to come out. So if 2 Na plus has to come out means 2 Na plus occupied positions are vacant now, and out of which only 1 Sr2 plus is there. 1 Sr2 plus which is going to occupy the position of 1 Na plus. Then another Na plus position will be unoccupied. Okay, that create the vacancy that is called cationic vacancy. Is that clear or not?
We call it cationic vacancy because Na plus is leaving, right, sir?
Sorry, cationic
We
vacancy.
are calling it cationic vacancy because Na plus is leaving, right?
Because of Na plus is not there. Okay. Because the cation is not there. That's what the cationic vacancy difference. Here it should be one cation should be there, but because of Sr2 plus impurity, 2 Na2 plus comes up. So 1 Na plus position will be occupied by 1 Sr2 plus. And what about the another position? Another position will be unoccupied, which means that it is empty. So this is the empty position. That empty position, which will be otherwise called as cationic vacancy difference. Is that clear?
I have one more doubt, sir.
Yes, yes, please.
So instead of SR2 plus or SRCl2, if we have NaF, sir, then
Yes.
chlorine and fluorine will take part, sir.
Chlorine?
That means chlorine will go to neutralize fluorine, sir.
No, we are talking about only voids now. We are not talking about that lattice points. Cations are
Okay,
only
sir,
occupying in voids. Okay. So where the impurity will go and occupy, impurity will go and occupy where the empty space is there. Okay.
It's understood.
Okay, fine. After which we'll finish it today class. We'll see next week. Fine. Okay. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.